Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at MENG 2022 math question 29. So I'm going to kind of be proving the answer to that exercise. That exercise is very complicated a little bit if you don't understand key concepts of similar figures. So actually the question was saying that we should consider ABC as a right angle triangle at a point A, and then AH is a height that is relative to the hypotenuse. Then the options were comparing the triangles ABC, ABH, and AHC, if they are similar or if there is a condition for them to be similar. And it turns out that the option was C, which says that these three triangles are similar provided the original triangle is isosceles. Okay, so that is what I'm going to be proving in this video today. All right, so we start by drawing our triangle ABC. Okay, so I have my triangle ABC. So this is A, because the right angle is at A. Then I'm going to label my points anti-clockwise in the conventional direction. So ABC. Now I'm going to draw AH. Okay, so H is a point that is on the hypotenuse such that the height AH is making an angle of 90 degrees with the hypotenuse. That's why they said AH is a height that is relative to the hypotenuse. So the segment AH and the segment BC are perpendicular. All right, so it therefore means that this other little angle here is also 90 degrees. Now I'm going to go ahead to give the side length of the respective sides. So I'm going to call this length X, I'm going to call this length Y, I'm going to call this little length Z, this other length A, this other length A, and then this other length B. Now when do we say that two triangles are similar? If two triangles are similar, then the angles are congruent and the ratio between their corresponding side lengths are all equal. All right, so I'm going to go ahead to introduce some angles in this figure. So I'm going to call this angle here theta. Okay, and I'm going to call this other angle here I'll call that angle theta. Then the other angle up this way, I'm going to call it alpha. Okay, now the next thing I'm going to do is alpha. Okay, if my writing is not really clear, please just bear with me. I'm not using a pen to write, I'm actually using my finger to write, so it's not really stable. Now let us begin with comparing triangle ABC and ABH. Then later we compare ABH and AHC. Then later we compare ABC and AHC, and then we conclude. So the three triangle, let us begin with, okay, let us compare. I don't think this color is really good, so let me try to use another one. So let's compare ABC and ABH. ABC and ABH. These are the three triangles you are going to compare now. Okay, so like we said, for two triangles to be similar, the angles in those triangles have to be congruent. First of all, congruent means basically the same, or one is a multiple of the other. And next, the ratio between the corresponding side lengths of these triangles are supposed to be equal. So for ABC, all right, let us talk about the hypotenuse, the opposite, and the adjacent, because ABC is this triangle, the original triangle ABC. All right, that is it, ABC. Now ABH, we have it ABH. That is ABH. That's the triangle ABH. You realize that ABC and ABH have a common angle, which is theta. So, and also they have a common angle which is also 90 degrees. In fact, both of them are right angle triangles, and then there is a common angle here which is theta. So definitely you realize that the other angles are going to be equal, because this angle here for ABH will be 90 minus theta, while this alpha here is also 90 minus theta. So the angles are already congruent. So let's just focus on their corresponding side lengths. Now, the hypotenuse of ABC is Z plus A. The hypotenuse of ABH is X, because this little a here is the adjacent, while B is the opposite. Now, the opposite of ABC is Y. That is the opposite to theta is Y. The opposite of ABH is B. All right. While the adjacent of ABH is A, and the adjacent of ABC is X. So let us begin with tan theta. So if I do the tangent of the angle theta, tan theta is going to give me, now if I consider ABC, just follow the diagram, opposite on adjacent. Opposite is Y, adjacent is X. But this tan theta is the same as, because the theta is still the same for both triangles. If you go to ABH, the opposite is B and the adjacent is A. Alright, so from here, if I want to do the ratio between corresponding side lengths, you realize that we are going to have B over Y to be equal to A over X. What is B and Y? B is the opposite to the angle theta of the triangle ABH, and Y is the opposite to the angle theta of the triangle ABC. Focus on the triangle. Alright, so B over Y, B and Y are all opposites. So that's why I'm doing the ratio, so that it gives me the ratio of the corresponding side lengths. Now, what about A and X? A and X, what is A? A is the adjacent of the smaller triangle ABH, while X is the adjacent of the bigger triangle ABC, and that is it. You realize that with this, you see that the ratio between corresponding side lengths are equal. Now, for us to conclude that these two triangles are similar, we have to talk about the hypotenuse of both triangles. Alright, the hypotenuse of the bigger triangle is Z plus A, while the hypotenuse of the smaller triangle is X. Alright, so let us do the ratio between Z plus A and X. To do that, I'm going to take sine theta. If we do sine theta, look at what we are going to have. If I do sine theta is going to give me opposite on hypotenuse. The opposite of the bigger triangle is Y, and the hypotenuse is Z plus A, which is still the same as, because it is still the same theta and the same sine. The opposite of the smaller triangle is B, and the hypotenuse is X, right? So from here, what do we have? We have that B over Y will be equal to X over Z plus A. So in conclusion, what do we have? B over Y is the same in the same equation. So B over Y will be the same as. So finally, we have that B over Y is equal to A over X, and it is still equal to X over Z plus A, right? And X is the hypotenuse of the smaller triangle, while Z plus A is the hypotenuse of the bigger triangle. So we have successfully proven that the ratio between their corresponding side lengths are all equal, and the angles are congruent for sure. So these two triangles are similar. So they are similar. Now let us go to the next. So I'm still going to withdraw the triangle. Then now we take the next pair and check the similarity property. So I still have my triangle. Here is H. I have A, B, C. This was X, this was Y, this was B, this is A, and this is Z. Here we have theta. In fact, let's just forget about that theta for now. So in this other case, we are going to be comparing, we are going to be checking the similarity of the triangles ABC and AHC. Alright, so we are going to do ABC and AHC. So let me withdraw. So A, B, C. ABC, this is H, and then AHC. So this is X. In fact, yeah, this is X, this is A, this is B, this is alpha, that is angle alpha there. This is Y, this is Y, and then this was Z. Voila. So that's what we have. So we are going to check the similarity of A, B, C and A, H, C. Okay, now we are going to begin with alpha. What is sine alpha and tan alpha for both of them? Okay, so sine alpha for the bigger one, which is ABC, is opposite, which is X, over hypotenuse, which is Z plus A. Now for the smaller one, because this is a 90-degree angle here, for the smaller one, which is AHC, the opposite is B, and the hypotenuse is Y. We clear Y is the longest. Okay, so if I go to tan alpha, okay, tan alpha is opposite. For the bigger one, the opposite will be X, and then the adjacent of the bigger one with respect to alpha is Y, because there's a 90-degree angle here. So the adjacent of alpha is Y. Now for the smaller one, the opposite to alpha is B, and the adjacent is Z. So we have to look for the ratio between the corresponding side lengths if they are all equal. All right, and then we conclude. Now from this tan alpha in this second equation, you realize that if I do x over b is going to give me y over z. All right, now up here you realize that x over b is equal to z plus a all divided by y. So in essence, we are saying that x over b is equal to y over z, and it is still equal to z plus a over y. This is a conclusion we have made. Now let us, what is x and what is b? All right, so clearly your x here and b, your x is the opposite of the bigger triangle, while b is the opposite of the smaller triangle. So this x over b is a ratio of the corresponding side lengths, because we have opposite over opposite. What is y and z? Your y here is the adjacent of the bigger triangle, which this very y here and this z here is the adjacent of the smaller triangle. So we have here y over z, big adjacent of big over adjacent of small. This one is opposite of big over opposite of small. What is z plus a for the big? Z plus a for the big is the hypotenuse. What is y for the big one? Y for the big one is the y for the small, sorry, because this all the denominators are for the small ones. Y for the small one is the hypotenuse. So you see, hypotenuse of big over hypotenuse of small. So you realize that the ratio of the corresponding side lengths, opposite and opposite, adjacent and adjacent, hypotenuse and hypotenuse, are all equal. So clearly these two triangles here are also similar. All right, so now we are left to talk about the similarity of the smaller triangles, that is ABH and AHC, because we have talked about ABC and ABH in the first slide. Now we have talked about ABC and AHC in this slide. Now in the last slide, we are going to talk about the similarity between ABH and AHC. Okay, so I'm going to withdraw. Okay, I'm going to withdraw. So this is A, B, C, this is H. Here we have our 90 degrees. I think this was X, this was Y, this was B, this was Z, this was A. Now here we have theta, and here we have alpha. Okay, now we have to check the similarity of the triangles ABH and AHC, these two triangles. Then I will now conclude. All right, so are these two triangles similar or not? This is where the condition for these two triangles to be similar is going to come in. All right, okay, so what is the hypotenuse of these two triangles? In fact, let me draw a little table of ABH and then AHC. So I'm going to put their corresponding side lengths. What is the hypotenuse of ABH? This is ABH. The hypotenuse is X. What about AHC? The hypotenuse is Y. So for ABH, hypotenuse is X, hypotenuse is Y. Now let us go to the opposite. All right, let us choose a unique angle. Or let's first of all talk about the adjacent. Anyways, talk about the adjacent. We need a unique angle. So, or anyways, not necessarily a unique angle. Let's just deal with the theta and the theta and alpha. So the adjacent of ABH, with respect to our angle theta is A, while the adjacent of AHC with respect to alpha is Z. So we have here A for ABH, and then for AHC is Z. Then finally you realize that the opposite for ABH is going to be B, while the opposite of AHC is still B. They have the same opposite, right, to their respective angles. Okay, so you realize that these two triangles are similar. All right, the two triangles are similar provided the ratio of the corresponding side lengths are all equal, because the question is, like, we are proving that if all three triangles are similar, then the triangle ABC is an isosceles triangle. So we have already proven that two pairs are similar. Now we are left to prove that this pair is similar. But in fact, we are left to justify, to use the property that this pair is similar to now justify that ABC is right, is isosceles. So like these two guys are similar provided the ratio of corresponding side lengths are all equal, which means that x over y should be the same as A over Z, should be the same as B over B. B over B is 1. All right, so in essence we are saying that x over y is equal to A over Z, which is equal to 1. Now if these two things are all equal to 1, then the first thing is that x over y is equal to 1, and the next is that A over Z is also equal to 1, which in turn means that x is equal to y and also A is equal to Z. All right, but if x is equal to y, then clearly ABC is going to be isosceles, because for an isosceles triangle we need that two side lengths are supposed to be the same. If this is x and this is y, which is still x, and there's a right angle, this is ABC, you clearly see that x and y are two side lengths of ABC and they are equal. So definitely ABC is an isosceles triangle. All right, ABC is an isosceles triangle. Now A is equal to Z. This man A is equal to Z, right? Anyways, it means that A plus Z is going to be maybe Z plus Z, which is 2Z. All right, so that is the hypotenuse, but we are just focused on the isosceles nature of ABC. So ABC is clearly isosceles for all three triangles to be similar. So for these three triangles to be similar to each other, then the original triangle ABC has to be an isosceles triangle, because using that condition we have seen that the adjacent has to be equal to the height, which is the opposite to the angle, if we call the angle here. So we have come to the end of the proof. Almost 20 minutes for one question. Anyways, I hope you guys have understood perfectly the idea behind this question. If you have any question, post in the comment section. Thank you guys for watching, and see you guys in the next video. Don't forget to like and comment.